Okay, so today's notes. We're doing section 5.2. This is the basics of probability. So we're going to talk about the basic probability rules. We're going to look at two-way tables and Venn diagrams, and we're going to talk about something called the general addition rule. On the cover of your packet, two things to remind you of. I always show you what you need to know on the calculator. There's nothing for this. And I also show you what you're going to do on the formula sheet. So these are two formulas on the formula sheet under the probability section. We're going to talk about these today and next class. So those are on the formula sheet. And you all have that green formula sheet that I gave you that is yours to keep. So it just would be good to maybe locate these formulas so that you know how to find them for your quiz and your test. This is where I want us to be right now. So here's the context. We randomly select a student who took the 2015 AP Stats exam, and we record the student's score. Here is the probability model. Okay, so the probability model gives all possible values of the variable. So in this case, that would be score. The only possible scores on the exam are 1 to 5. And then it gives their associated probabilities. That's what makes it a probability model. Or sometimes you'll see distribution, a probability distribution. You might be asked, why is this a valid model? What you need to know is those probabilities are all going to sum to 1. Because those are the only possibilities. So in your homework, when you see why is this a valid probability model, it's because the probabilities sum to 1. First thing you have to be able to do, which you probably have done before or can figure out, is basic probabilities. So find the probability that a chosen student scored 3 or better. You need to show work. So if we use X to be the student's score, we are looking for the probability that the student's score is 3 or better, so you could write it that way. Or you could write out the individual possibilities, so that means the student scored a 3, a 4, or a 5. That is considered showing work. You have to show that. And so then we're just taking 0.252 and adding 0.192 and 0.134. Which is 0.578. Okay, if we find the probability that the chosen student did not score a 1, we're looking for the probability that they didn't get a 1. So one possibility is I could add up 2 and 3 and 4 and 5. Or what is more efficient than that? 1 subtract the only case that we don't care about, which is 1. So we get 0.764. So that should not be new. Okay with that? Or at least should be intuitive, I would say. Okay, so let's move on. Vocab word, sample space. The sample space displays all possible outcomes. So yeah, displays all possible outcomes. A sample space is normally displayed in a list or what we call a tree diagram. So we're going to do an example where I show you how to map out a sample space. So here's our example. A library has 5 copies of a certain textbook on reserve, of which 2 copies, numbered 1 and 2, are first printings, and the other 3, 4, and 5, are second printings. A student examines these books in a random order, stopping only when a second printing has been selected. So we're going to display the sample space. I'm going to do it in a tree because I think that makes the most sense. So the way we're thinking about it is we have to picture in real life we're standing in front of this shelf and we're picking a book off the shelf. How many options do we have for that first book? 5. Okay, so then we're going to draw our 5 possibilities. So this is the first book we take off the shelf, and it could be book 1, 2, 3, 4, or 5. Now, once we take the book off the shelf, we're done with it. It doesn't go back on. So once we take the book off, there's now 4 available. It says we're stopping only when a second printing has been selected. So if I choose book 1 and put it off to the side, am I going to keep going?
Yes.
Yes. And then I will have 4 options. So from here, I could choose books 2, 3, 4, or 5. Now, if I choose book 1 and then book 3, I'm done, because book 3 is a second printing. But if I choose 1 and 2, those are both first printings, so then I have to choose again. So this would be 3, 4, 5.
This is difficult to
Yeah.
draw and both keep small.
So when you get to the end is one possibility. So one possibility is 1, 2, 3, 1, 2, 4, 1, 2, 5, 1, 3, 1, 4, 1, 5. Similar idea. If the first book that I choose is 2, that's a first printing, I'm going to choose again. So then my options are 1, 3, 4, 5. If I choose 2 and then 1, they're both first printings, so I have to go again. And I would stop when I get 3, 4, or 5. Now, right off the bat, if I choose book 3, I'm done. Book 3 is a second printing, so that's it. I don't choose again. So this is the sample space. The other way that you can show that sample space is writing it out like a list. So if I go with this first possibility, that would be books 1, 2, 3. Or I could have 1, 2, 4, 1, 2, 5, 1, 3, 1, 4, 1, 5, so on and so forth. Now, you wouldn't do ... You would actually write all of them out. I'm not going to do that because I hope you get the point.
That gets big at some point.
Yes. In your homework, you're going to have to write out the sample space. Sometimes it will say just display the sample space. You can choose that. Sometimes it will say use a tree diagram. Sample space is helpful so that you can look at questions like B, where you're looking at specific outcomes. So B says, what outcomes are contained in the event A that exactly one book is examined before the chance experiment terminates? So A, which we call an event, the only cases where we look at one book only is if we choose 3, 4, or 5. So that would be if I choose book 3, book 4, or book 5.
Oh, for a second I got a bit confused because of the wording of the exactly one book examines before the experiment terminates. Because it says the experiment terminates when you choose a...
Yeah, I get you.
Wording.
And then C. What outcomes are contained in the event C that the chance experiment terminates with the examination of book 5? We're looking at our tree every time we end at book 5. So book 5 here, book 5 here, 5 here, 5 here, 5 there. So those are the ones that we are outlining. So we could have 1, 2, 5, 1, 5, 2, 1, 5, 2, 5, and then just book 5. Okay with that? Okay. We're going to finish this page and then we'll take a break. Okay. What is a probability model? We wrote this on the previous page. Probability model. shows all possible values of the variable. And the associated probabilities. How do you verify that the probability model is legit? We also wrote that on the previous page. The probabilities sum to 1. Not greater than 1, not less than 1. An event is what we saw above. A is called an event. C is called an event. An event is a subset of the sample space. In other words, it is a certain set of outcomes from the sample space. Okay. Five basic probability rules. The probability of some event, like event A, is the number of outcomes in A divided by the total number of outcomes. Here's what's really important, though. That is assuming all the outcomes are equally likely. Second one, any probability has to be between 0 and 1. Probability can't be negative, probability cannot be greater than 1. So we've talked about that already. Do not tell me that a probability is 20%. That doesn't make sense. The probability is 0.2. We've talked about on your calculator, sometimes you're going to get scientific notation. So the probability is not 2.4. It might be 2.4 times 10 to the negative third. 0, the event is not going to happen. 1, it's guaranteed to happen. So then this one should be intuitive. The probability of all outcomes or in other words, the probability of the sample space is 1. That's all the possible outcomes. One of them has to happen. The probability of event A not happening. So we have the probability of A, but the probability of A not happening is 1 subtract the probability of A. So for example, on the previous page, we had the probability that X was not 1, that the student did not score a 1. And so we did 1 subtract the probability that they did get a 1. That's just that property. Okay, and then the last basic rule is if events A and B are mutually exclusive, which we're going to talk about in a minute, then the probability of A or B is equal to the probability of A, add the probability of B. This is by far the most misused property or rule. This only applies if the events are mutually exclusive. Again, we're going to talk about what that means in a minute. If you're looking for the probability of A or B, though, you can only add them if the events are mutually exclusive. So of course this leads us to, what does it mean for events to be mutually exclusive? It means they cannot occur at the same time. Another term for this that you're going to see is disjoint. So if you see disjoint, mutually exclusive, those are the same. You need to know both. Just means they can't occur at the same time. We're going to write one other thing down. So looking at a Venn diagram, if A and B are mutually exclusive, this is what it would look like. They don't share any common outcomes. So these are mutually exclusive. If they were not mutually exclusive, you would see something like this. And that is because they do share these outcomes between them. Okay. Questions for me before we take a break? Okay, moving forward. Rest of these notes, mostly examples. This is when we finally get into the numbers and calculating probabilities. So you're actually going to need your calculator now. First example that we're going to do. In 2012, fans at the Arizona Diamondbacks home games would win 3 free tacos from Taco Bell if the team scored 6 or more runs. In the 2012 season, the Diamondbacks won 41 of their 81 home games and gave away free tacos in 30 of their 81 home games. In 26 of the games, the Diamondbacks won and gave away free tacos. Let W equals win and T equals free tacos. Choose a Diamondbacks home game at random. First thing we need to do is summarize the data in a two-way table. Here's what a two-way table looks like. We have 2 events that we need to represent. One is winning. So at the top, we're going to say, did they win? One column is yes, they won. One column is no, they did not. And then the other one is, did they give away free tacos? One row is yes, one row is no. And then we need to put in all of the numbers that we are given. So it says the Diamondbacks won 41 of the 81 home games. So that gives us 2 pieces of information. First, it tells us that the table needs to sum to 81, that there are 81 games total. They won 41 of the home games. That 41 goes here. So that means between these 2 boxes, I have 41 games I need to put. And then it also says they gave away free tacos in 30 of the 81 home games. So the 30 goes here. Again, those 2 boxes in the row have to add up to 30. And then the key is this one right here. In 26 of the games, they won and gave away free tacos. So that 26 goes here. Yes, they won, and yes, they gave away free tacos. That now gives us all the information we need to fill out the rest of the table. If that first row has to add to 30, that means I need a 4 here. If that first column has to add to 41, I need a 15 here. And then if I add 26 and 4 and 15, that's 45 games, which means 36 games go here. And then it's just a good idea just to double check. That first column is going to add to 40. And we see, okay, 41 and 40 do add to 81. That second row is going to add to 51. Again, that gets us to 81. So that is the two-way table. That is what we're then going to use to answer these following questions. What is important in these questions that follow is not necessarily the answer, but the notation. So I'm going to teach us a lot of notation. We're going to write each of these probabilities using W and T. So find the probability that they did not win the game. So the way we write that is the probability of W complement. Okay, so that little c stands for complement, and that just means not. So the probability that they did not win the game, out of the 81 games, there were 40 that they did not win. I'm just reading the table. So out of the 81, 40 games they did not win. Find the probability that they won and there are free tacos. The way to write that, probability of winning and free tacos. So this symbol is the and symbol. So again, out of the 81 games, if I look how many did they win and they gave away free tacos, that happened 26 times. This is considered your work. If you want to convert to a decimal, you can. You have to show the fraction though. So on the AP test, if you give a decimal and you don't give the fraction, you're not going to get credit. So you got to make sure you get that fraction also. And then in D, find the probability that the Diamondbacks win or there are free tacos. So the probability of winning or free tacos. So this is the or symbol. Well, let's add it up first and then we can talk about the mistake people make. Out of those 81 games, we need to look at how many of the games in the table did they win? So that would be here and here. Or there were free tacos. Well, that's also free tacos happened here. So if we add up those three, that would be 26, add 4, add 15.
Yeah, 50. No, 45. Yeah, 45.
So we get 45 out of 81. Okay, what I want to talk about. What a lot of people will do is they will incorrectly use that rule from the previous page. And they'll say, okay, probability of W or T. Well, I can just take the probability of W and add the probability of T. What is the probability of W?
41 out of 81.
41 out of 81. What is the probability of T? 30 out of 81. If we add those, do we get the same answer? No. Why not? That answer is right. That's a 30. But why is this wrong? They overlap. They are not what? Mutually exclusive. So this does not work because W and T are not mutually exclusive, aka they overlap. Okay, so the question then is, what do we do if it's an or and they're not mutually exclusive? That's what leads us to the general addition rule. The general addition rule says the probability of A or B is the probability of A, add the probability of B. Okay, if we look at our table, and we use the W and the T. If we look at the probability of W, that is these numbers. If we look at the probability of T, it's these numbers. So what is the issue? What is being double counted?
The probability
and
of
tacos.
both occurring.
The probability of both occurring. So this is what is being double counted. So what we have to do is we have to subtract the and. So that is the general addition rule. And just to remind us of the symbols, this is the or, this is the and. Some things for you to know. First of all, this is on the formula sheet. So you do not need to remember this. The second thing to know is when we say or, it is not a strict or. So if we draw a really small Venn diagram here, if this is A and this is B, and I ask for A or B, it's all of this stuff. So do you guys see how it still includes this piece in the middle? So when we say A or B, it still allows the possibility of both happening. Okay. Can I keep going?
Sure.
Okay. So moving on, another probability. Find the probability that the Diamondbacks win given there are free tacos. This is more symbols. Find the probability that they win given is a vertical line, there are free tacos. So this bar is a given. So the way to look at this is we look at the given first. In how many games were there free tacos? 30. That is the numerator then. All we care about is the free tacos. And then out of those 30 games, how many times did they win? 26. Now, if we look at F the other way, find the probability that there are free tacos given that they win. So it's the same two events, but reversing the order. Okay, this time we're only looking at the games that they won. How many games did they win? 41. And how many of those 41 games were free tacos given away? 26. So I want you to notice, when we reverse the order, the numerator stays the same, the denominator does not. This is called a conditional probability. This is called a conditional probability. So conditional probability is the probability of some event knowing another event has occurred. You guys have already seen conditional probabilities. Do you remember looking at two-way tables at the very beginning of the year? And it was something like, we might have organized people by hair color and eye color. And then you made a stacked bar chart for one variable only. Like looking at only the blue-eyed people, make a stacked bar chart for hair color. And then looking at the brown-eyed people, make a stacked bar chart. That's a conditional probability. The condition being eye color. Okay, so there is a formula. The probability of A given B. We can figure this out from above. What is this 26 in regards to W and T? We can't see the table, but what is
where both of them occur.
where both of them occur? So the numerator is the probability of A and B occurring. The denominator then, this 30 is how many times there were free tacos. This 41 is how many times they won. So the denominator is the given. Okay. Questions? Comments? Okay. Next word is how do we tell if two events are independent? So here's the idea with independent. Independent events occur when knowing the outcome of one event does not provide additional information about a second event? You can think in terms of a scatter plot, showing an association. With scatter plots, we were looking to predict something. Let's say that I wanted to predict your height. If I measured the size of your foot, do you think that there's a relationship between the length of your foot and how tall you are? Right? So I could probably use the length of your foot to predict your height. Now, if I measured the length of your hair, on the other hand, could that help me predict your height? No. So we would say hair length and height are independent. Knowing your hair length does not affect or does not give me any additional information about your height. Okay, the way to tell is we have to look at a conditional probability. So this is the probability of A happening given B has already occurred. If the events are independent, B occurring means nothing to me. It doesn't give me any extra information. So that should just be equal to the probability of A. Again, if they are independent. Okay, so are the events T and W independent? Well, we can see right above, we have the probability of T given W is 26 out of 41. If the events are independent, then W happening should not affect the probability of T. So if the events are independent, then the Diamondbacks winning should not affect at all the probability of free tacos. So the probability of free tacos we saw above, it happened in 30 of the 81 games. I think it's helpful to convert these to decimals. So that first one is about 0.634. Second one is about 0.37. So we would say no, they are not independent because the probability of T given W is not equal to the probability of T. That should make sense in context. If we choose a game at random, the probability that they gave out free tacos is probably going to be pretty low, right? If they gave out free tacos, the team had to have scored like 6 or more home runs. That's not very likely. But if we know that they won, that's a much higher likelihood then that they scored those 6 or more runs. Questions for me before you all do an example? We are going to skip this stuff at the top. I would like you to do this entire one at the bottom. So it's basically what we just did. I want you to define variables. You're going to set up a two-way table, and you're going to calculate a bunch of probabilities. Please use correct probability notation. So I want you to do this with the person next to you or the people next to you. Good luck. Here are the answers that I got. Okay, I care about not only your answer, your notation. So I used S and O. I know you all use different things. For C, the and, remember, is this symbol, whereas for D, the or symbol is this one. We should have showed work of some kind. You do not have to simplify the fraction. You don't have to simplify it. You don't have to give a decimal. So I wouldn't even bother.
How close do like the two probabilities have to be?
Great question. So first of all, make sure that these are the ones that you compared. I saw a lot of us just say yes or no with no numbers. You need to have numbers. So for our class, in order for the events to be independent, these two have to be exactly the same. So we're not going to say, oh, they're pretty close. Real life statisticians, there is like a certain margin of error that they'll allow, but we want them to be exactly the same. Yes?
Doesn't that if you like flip them? If you know what I'm saying? Like, you do P of like others over the graduates instead?
P of,
Well, it gives you like the same thing.
so there are other possibilities. You could do this. You just have to make sure you compare it to the right probability then.
So it'd be equals P of X, right?
Correct. Yeah, there's a whole bunch of different
So as long as you
possibilities.
do that, it doesn't
Yep.
matter.
So again, the reason they are not independent is the probability of owning a home is 0.68. As soon as I tell you though that they graduated high school, it gives you more information about whether or not they own a home. How do we feel about that? We feel okay? I need like probably 7 more minutes of your time. That okay? Okay. So what we're going to do is we're going to go up to the top that we skipped. And we are going to just talk a little bit more about mutually exclusive and independent. There are a lot of people that mix up these two terms. And so I want to make sure we understand the difference between them. Mutually exclusive, remember the other term you might see is disjoint. And that means they cannot happen at the same time. So if we were to fill in this table so that A and B are mutually exclusive, what is the first number that we should put in?
0 in the AB's spot.
0. They cannot happen at the same time. So then if that B row has to be 30, this has to be a 30 then. This will have to be a 60, that'll have to be a 10. That is mutually exclusive. They cannot happen at the same time. Okay. Independent, on the other hand, the way that we just showed it in symbols is the probability of A given B has to be equal to the probability of A. So we're going to use that on the table. Probability of A. So if we look at our table, there's 100 outcomes total. 60 of those are in A. The left side is where we need to make sure we use the formula. On the left side, in the denominator, is going to be the given, the probability of B. Our given on the table, there are 30 outcomes in B. What goes in the numerator is A and B, which is what we don't have. That would be this box right here. So we can just put an X there then. If we solve that proportion, so we cross multiply, right, you're going to get 100x is equal to 1800. So that box then is 18. Then we can fill in the rest of the table. So that would make this a 12. This would be a 42. And this would be a 28. These are not the same thing. It is not possible, actually, to be independent and mutually exclusive at the same time. And there are a lot of events that are neither one. Mutually exclusive, you can normally tell just by context. You don't really need numbers. Independent is the one that you have to check using numbers. How do we feel about probability? We feel okay?